Hello and welcome back to Steven Data. Today in this video I want to talk about hypergeometric distribution and its properties like mean and variance. Okay, let's get to it without killing time. Suppose that a day's production of 850 manufactured parts contains 50 parts that do not conform to customer requirements. 2 parts are selected at random without replacement from the day's production. Let A and B denote the events that the first and second parts are non-conforming, respectively. From counting parts in the sample space, the probability of B given A equals 49 over 849, and the probability of A equals 50 over 850. Consequently, the knowledge that the first part is non-conforming suggests that it is less likely that the second part selected is non-conforming. Let X equal the number of non-conforming parts in the sample. Then, the probability of X equals 0 is the probability of both parts conform, and that is equal to 0.886. The probability of X equals 1 is the probability that the first part selected conforms and the second part does not, or the first part selected does not, and the second part selected conforms, and its probability is equal to 0.111. Then, the probability of X equals 2 is the probability that both parts do not conform, and that is equal to 50 over 850 times 49 over 849, and it's equal to 0.003. This experiment is fundamentally different from the examples based on the binomial distribution. In this experiment, the trials are not independent. Note that in the unusual case that each unit selected is replaced before the next selection, the trials are independent and there is a constant probability of a non-conforming part on each trial. Then the number of non-conforming parts in the sample is a binomial random variable. But the samples are often selected without replacement, although probabilities can be determined by the preceding reasoning. A general formula for computing probabilities when samples are selected without replacement is quite useful. The counting rules presented in the combination and permutation video can be used to justify the following formula. A set of M objects contains K objects classified as successes, M minus K objects classified as failures. A sample of size N objects is selected randomly, that is, without replacement, from the M objects where K and N is less than or equal to M. The random variable X that equals the number of successes in the sample is a hypergeometric random variable, and its probability mass function is equal to K choose X times M minus K choose N minus X over M choose N. The expression the minimum of K and N is used in the definition of the range of X because the maximum number of successes that can occur in the sample is the smaller of the sample size N and the number of successes available K. Now, let's see an example. A batch of parts contains 100 from a local supplier of circuit boards and 200 from a supplier in the next state. If 4 parts are selected randomly and without replacement, we are interested in the probability that they are all from the local supplier. Let X equal the number of parts in the sample space from the local supplier. Then X has a hypergeometric distribution, and the requested probability is the probability of X equals 4, and that is equal to 100 choose 4 times 200 choose 0 over 300 choose 4, and it's equal to 0.0119. Now, what is the probability that 2 or more parts in the sample are from the local supplier? The requested probability is equal to the probability of X is greater than or equal to 2, and that is equal to 100 choose 2 times 200 choose 2 over 300 choose 4 plus 100 choose 3 times 200 choose 1 over 300 choose 4 plus 100 choose 4 times 200 choose 0 over 300 choose 4, and that is equal to 0.407. And now, what is the probability that at least one part in the sample is from the local supplier? The requested probability is equal to the probability of x is greater than or equal to 1. And this probability is equal to 1 minus the probability of x equals 0. That is 1 minus 100 choose 0 times 200 choose 4 over 300 choose 4. And this probability is equal to 0.804. Now it's time to get familiar with the mean and the variance of the hypergeometric distribution. If x is a hypergeometric random variable with parameters m, k, and n, then the expected value of x is equal to n times p, and its variance is n times p times 1 minus p times m minus n over m minus 1, where p equals k over m. You can clearly see that for a hypergeometric distribution, the expected value of x is similar to the mean of a binomial distribution, but the variance differs from the result of a binomial distribution by this term, which is called the finite population correction factor. Now, as always, let's see an example of the mean and the variance of the hypergeometric distribution. In the last example, the sample size is 4. The random variable x is the number of parts in the sample from the local supplier. Then p equals 100 over 300, that is 1/3. Therefore, the expected value is equal to 4 times 100 over 300, and that is equal to 1.33. And its variance is equal to 4 times 1/3 times 2/3 times 300 minus 4 over 299, and that is equal to 0.88. But before wrapping up the video, please pay attention to this point. Sampling with replacement is equivalent to sampling from an infinite set because the proportion of success remains constant for every trial in the experiment. As mentioned previously, if sampling was done with replacement, x would be a binomial random variable and its variance would be n times p times 1 minus p. Consequently, the finite population correction represents the correction to the binomial variance that results because the sampling is without replacement from the finite set of size m. If n is small relative to m, the correction is small and the hypergeometric distribution is similar to the binomial distribution. In this case, a binomial distribution can effectively approximate the hypergeometric distribution. Now it's time to wrap up the video by reviewing what we have learned so far. First, we saw that the hypergeometric distribution is like the binomial distribution except for the sampling without replacement aspect. Actually, when you sample without replacement, the probabilities change with each subsequent trial. Conversely, the binomial distribution assumes the chances remain constant over the trials. Then we got familiar with its probability mass function, which was equal to k choose x times m minus k choose n minus x over m choose n. And then we saw its mean and variance, which were equal to n times p and n times p times 1 minus p times m minus n over m minus 1 respectively. And that is done. Congratulations! Now you know what the hypergeometric distribution is and you can solve and model real-world problems with its help. And remember, for more information about other distributions, you can check out this playlist. Finally, if you like this video, please hit that like button, and if you are interested in statistics, data science and machine learning, please consider subscribing to this channel. By the way, if you have a question about the fields I mentioned, comment it down in the comment section, and don't forget to share my videos with your interested friends. I hope this video helped you a lot, and until the next video, happy learning!